Today we are going to be discussing how to model rigid diaphragms in STAAD.Pro and understanding the diaphragm behavior and how it may affect the rest of your modeling steps. Now, before we go any further, let me start by introducing myself. My name is Sabrina Tedeschi, and I'm going to walk you through this workflow today. Just to give you a little background on myself, I am a senior structural application engineer here at Bentley Systems. I've been with Bentley Systems for over 12 years, and I typically conduct training courses and create training programs for all of the products within the RAM and STAAD product lines. I am a structural engineer, and before working for Bentley Systems, I did work in the industry for an architectural engineering firm, and I designed large commercial structures out of a variety of materials, including steel and concrete. I did also use RAM and STAAD in my life prior to joining Bentley Systems. Now let's go ahead and introduce our topic today. Today we're going to be talking about rigid diaphragms in STAAD.Pro. When I'm talking about rigid diaphragms, my focus for today is going to be using the floor diaphragm specification. It is a nodal specification, and what I'm going to do is I'm going to walk you through the workflow on that particular topic. So what we're going to do is we're going to start off small today. I'm going to start off by just going through the modeling workflow for creating those rigid diaphragms. In that process, we're going to talk about modeling your rigid diaphragms, specifying them at different levels of your structure. And we're also going to talk about some other modeling steps that you're going to need to include in that workflow, such as setting up a reference load case with your masses to complete that process. We're also going to take a look at some analysis commands that we also have available when you're using a rigid diaphragm. These will include things like checking the stiffness of your floor diaphragms and also checking for irregularities. And we're also going to move that a step further using that irregularity information to determine which type of analytical procedure could be appropriate for us depending upon those results of a rigid diaphragm system, and what type of eccentricity needs to be included. All of this is kind of tied together with that whole idea of rigid diaphragms. And I'm going to switch your attention over to my STAAD.Pro application. So what we're going to do, what I'm going to do is I'm going to redirect your attention to my STAAD.Pro model. And let's go ahead and start our workflow today. Now, as I mentioned, what I'm going to be doing is I'm going to be showing you the complete workflow for modeling floor diaphragms using the floor diaphragm specification. We're also going to go through a few of the extra options that are available or things you might want to consider when doing a floor diaphragm. Again, this would be things like, do you have any irregularities? What type of seismic loads are you permitted? How do you assign eccentricity to those seismic loads? All of this is wrapped up together. So what we're going to do is we're going to start pretty slow, and we're going to start by just modeling our rigid diaphragms. So what I'm going to do is in my workflow page control area, I'm going to go to the specification tab that's right above my view window. When I select that tab, I'm going to notice that the specification dialog is going to be available in my data area. I'm also going to notice that automatically STAAD.Pro redirected my attention to the specification tab in the ribbon toolbar. Of course, I am using STAAD.Pro Connect Edition for this particular workflow. Now, for my particular model, it would be important to understand at which level my rigid diaphragms will be entered on. So my first floor level in this particular model is at y equals 10 feet. My second level is at y equals 20 feet. And my third level is at y equals 30 feet. When using the floor diaphragm specification, you are going to enter a floor level. Another alternative would be that you could also select the nodes first. I'm going to go ahead and enter the vertical level of my floor system. Now, to assign this specification, what we're going to do is go to the specifications dialog and click on the node item. Now, we have two different node specifications that are available within STAAD.Pro. The first is your master slave specification. Now, this is the older version or older way of modeling rigid diaphragms or rigid links within STAAD.Pro. This was also available in STAAD.Pro V8i and is available in STAAD.Pro Connect Edition. Now, although the master slave specification is available to you if that's your traditional form of using rigid diaphragms or simulating rigid diaphragms, it doesn't unlock the full capabilities or allow you to really understand a full rigid diaphragm like the floor diaphragm command does. So let's go ahead and advance to your floor diaphragm command, and let me go ahead and explain some of the differences that will be available. First of all, with the floor diaphragm command, we can include a few extra things. The first most obvious benefit of using the floor diaphragm command is that I can ask the program to calculate the center of mass for me for each level of my structure. This can be hugely beneficial. Now, with allowing the program to calculate the center of mass for you, you also get the added benefit of being able to consider extra eccentricity within your seismic loads. So within your seismic loads, you have two different types of eccentricity. You have accidental eccentricity and inherent eccentricity. Now, inherent eccentricity happens when your, say, your seismic loads are applied to each level of the structure at your center of mass, but then resisted through your center of rigidity. Well, if your center of mass and your center of rigidity are not the same location, you could create an additional moment arm that is going to add some moments to your seismic load. And the floor diaphragm will have that capability. This will unlock the inherent torsion available within your system. The third major benefit that we're going to talk about is the ability to check for some vertical and horizontal irregularities to kind of understand or have STAAD.Pro assist you in determining what else is needed per the code for incorporating seismic loads within your system. So the first thing I'm going to do is I'm going to start by naming my diaphragm level. I'm going to start at level number 1. Now, a few things that we need to note with STAAD.Pro is that the diaphragms must be specified in ascending order. You're going to start at the lowest level of your structure and work up. That's the way the program wants you to specify it. The second piece of information we should understand is that the floor diaphragm specification cannot be used when you use a set Z up command. So typically your vertical axis in STAAD.Pro is your Y axis, but you do have the capability to instead tell the program that you want to use the Z axis as your vertical axis, and you do that by specifying the set Z up command. Now, unfortunately, certain areas of the program, including the floor diaphragm command, are not appropriate for a set Z up condition. So it's important that you don't change the default orientation of your model, that Y is your vertical axis. The last thing that we should note is that slope diaphragms are not supported. You're going to see all of my floors are flat within this particular model. So I'm setting my floor diaphragm as number 1. I'm entering the height as Y equals 10 feet. That corresponds to the first level of my system. Now, again, I could assign it to some selected nodes. I haven't selected any nodes, so what it's going to do is it's going to search all the nodes at that Y elevation. Had I wanted to specify only a certain number of nodes, I could either select them or enter them within a certain range. So any within this X or Z coordinate would be included, but then anything outside of there wouldn't. For me, I'm going to say the entire floor system is appropriate. So I'm just going to say Y equals 10 feet. Let's go ahead and click the Add button, and then we'll close out of that dialog. So what I'm going to do is I'm going to continue on with the rest of the floor levels. Again, I'm going to go back to the node level. I'm going to say this is going to be diaphragm number 2, height Y equals 20 feet. And again, I'm going to ask it to calculate the center of mass. And I'm going to finish that off with my top level. Now, if you notice, I'm getting a little bit of a note when I'm specifying these diaphragms. I don't want to skirt over that. The thing was, I was practicing this before this session, so STAAD.Pro is kind of recognizing that I've already kind of specified that diaphragm. It's not a big deal. If I closed out of this model and came back in, it would retain all that information. This won't yield an error or a warning for me. It's just the fact that I practiced this right before we joined this session. So what I've done is I've gone ahead and specified a rigid diaphragm at each of those levels. So I have level 1, diaphragm number 2, and diaphragm number 3. Now, when you specify the floor diaphragm command, of course, we're going to ask the program to calculate the center of mass for us. And how is it going to go ahead and do that? Well, it needs some additional information from me. And when using a floor diaphragm command or specification, is absolutely necessary to also create a mass reference load case. You're going to define all the masses of your structure that are appropriate for determining the center of mass of your system. So let's go ahead and proceed on to that area. So I'm done with my specifications. I'm going to go to my loading area. I'm going to expand my definitions and my load case details section. Now, when preparing your model for floor diaphragms, I'm going to create a reference load case for masses. So I'm going to highlight my reference load definitions, click my Add button, And I'm going to create a reference load case for mass. The loading type, which is super important when defining your masses, is you're going to specify it as a mass. This is what's going to tell the program that this is the type of load it is going to be used in, and it will search for this load case when it needs to find out what the mass of the structure is or calculate the mass of the structure. So what are the other load cases that might use this load for us? Well, when using the floor diaphragm specification, this load case is going to be used to calculate the center of mass of each level. If I was also creating a static seismic load case using the equivalent lateral force procedure in STAAD.Pro, it can also search for that mass for that purpose. And then finally, if I have any dynamic seismic load case using, say, the modal response spectrum procedure, it can also use this mass reference load case. So this is the kind of thing that's going to be used in several areas of the program, depending upon if they're applicable. So I'm going to create this reference load case, and then I'm going to populate it with the mass of the structure. Now, this is where you are going to have to refer to your local building code to determine what is necessary for including in the mass of your system. Do you need to include just the dead load of your system? Do you have any storage loads or a portion of snow loads or partition loads that are also applicable? So this is where you're going to refer to your building code to determine what needs to be included in mass. For my structure, I'm going to say that the self-weight of my structure, basically the dead load of my structure, should be included. And I'm also going to add a little bit of superimposed load in accordance with how the masses are laid out in my system. So I'm going to add this reference load case. I'll go ahead and click the Add button. And then from this area, I can see all of the different options I have available for modeling that mass. Now in STAAD.Pro, all masses that are capable of moving should be modeled as loads applied in all possible directions of movement. Even if the loading is known to be only in one direction, there's usually mass motion in other directions at some or all of the joints in your particular model. So joint moments that are entered will be considered to be weight moments of inertias. And additionally, you're going to enter them considering two things. First of all, you're going to typically enter a consistent sign for all of the masses within your structure. I typically enter mine all with absolute value format. The reason this is important is because you want your masses to all be added together. If you have inconsistent signs, they may eventually cancel each other out. The next is you need to consider the directions of motion. And I'm going to say that for my structure, I'm going to enter my masses in the three global axis directions, the X, Y, and the Z. So I'm going to start with self-weight, and I'm going to model this in the X, Y, and Z directions. And for my particular model, I'm also going to say I have some superimposed load that I also want to consider, and I'm going to enter that in terms of nodal loads. Now, this is a step of your workflow where every structure may be different depending upon how your masses are laid out in your structure. So I accomplished what I'm looking for through the self-weight load item and also a nodal load item. You may consider things like floor loads or other reference loads to be more appropriate for how your masses are laid out. So you definitely want to take a look at that. So let's finish this off by assigning it to the model. And I'm going to save my model. The last thing I'm going to do at this point is go ahead and take a look at the analysis page. You can see here my floor diaphragms were added. I have that reference load, and I have a perform analysis command. Now at this point, what I like to do for floor diaphragms is I like to walk into it so we can keep seeing information added to our output file. And the output file is where we're going to be getting most of our results for today's session. So as soon as my analysis is done, I'm going to go ahead and look and see that I have 0 errors and warnings in my particular model. So let's go ahead directly to the output file and see what we have available to us. Now we do have a note available. It's just letting us know that the mass model formed will be using the seismic response time history loading, if any. So this is basically just letting me know that I noticed you had a reference load case for mass, and I'm going to be using that in your seismic loads, your response spectra, or time history loading if applicable. Okay, I actually don't have any of that information in my model yet, so I can go ahead and disregard that note. And let me go ahead and proceed on to the floor diaphragm table. Now, the floor diaphragm table will go ahead and be populated automatically for you in the output file when you create a floor diaphragm within the system. Within this floor diaphragm, I have a few pieces of information. First of all, I can see the floor level that each was modeled at. I can see it defined it as a rigid diaphragm. I can see the floor weight of each system. Now, again, this is going to be using my reference load case for that. And it went ahead and calculated the center of mass. It's going to give me an X and Z coordinate. Now, what the program does is, so the major difference between the floor diaphragm specification and the master slave specification is that I don't need to go ahead and tell the program where a master node is located. What the program is going to do is it's going to establish the location of the center of mass. And if there isn't already a node located there, it's going to internally create a node at that location. So it's letting me know that these are the 3 new nodes that it created to kind of represent where my center of mass is. So everything so far looks pretty good for me. I just wanted to show this table because this is kind of a key piece of information that's now available to me, the ability to calculate the center of mass. Now, that center of mass for each rigid diaphragm is included by the program automatically, but I may also be interested in, if eventually I'm going to be taking a look at things like seismic loads, I may also be considered in where is my center of rigidity in the program. Now, that's not automatically given to me in the output file, but I do have the ability to tell STAAD.Pro that I do want that information. So to access that information, I'm going to go to the Analysis and Design tab in the ribbon toolbar, and I'm going to go to the Post Analysis Commands area. Let's go ahead and click on Define Commands. Now here I'm going to find a command to print my center of rigidity in my output file. So the lateral force at each floor, as generated by earthquake and wind loading, will act at the center of mass of each floor, which is modeled as a rigid floor diaphragm and resisted through the center of rigidity. The center of mass of each floor is defined as the mean location of the mass system of each floor level, and the mass of the floor is assumed to be concentrated at this point when the floor is modeled as a rigid diaphragm. The distance between the center of mass and the center of rigidity will create a lever arm for the natural torsional moment for seismic loads when this option is selected. So what I'm going to do is I'm going to tell the program I want to find out where my center of rigidity is. I'm going to click the Add button and then click Close. Now again, let's go ahead and save our model. And I'm going to run my analysis again. And again, go directly to the output file. Now here I have an additional option available here. So diaphragm center of rigidity. So I have a quick link to that area. So it's gone ahead and calculated where the center of rigidity is for each floor level. This is only appropriate when you have a rigid diaphragms in your model. And it's gone ahead and given me the X and Z coordinates. As it turns out for my particular model, that my center of rigidity is actually very close to where my center of mass is, so I'm not anticipating a large moment being generated there. I did do a run with this sample model beforehand, adding some brace frames to one side of the structure but not the other, and of course then you start seeing a little bit of additional moment being added. Okay. Let's go ahead and move forward. And what I'm going to do is I'm going to take a look at some diaphragm options that I also have available to me. So in the Analysis and Design tab in the ribbon toolbar, I'm going to go to Miscellaneous Commands, and I have a floor diaphragm options area. Let's go ahead and click on that. Now this is what I was telling you beginning. You may want to consider upgrading to at least STAAD.Pro Connect Edition version 22 Update 2. Prior to version 22 Update 2, we had a soft story check, but we did not have an irregularity check in the program. That was added in Update 2. So I'm going to strongly encourage you to go ahead and upgrade if you have not already. So let's go over this dialog. The first thing I'm going to do is I'm going to specify the design code that I'm interested in. I'm in the United States, so I'm going to go ahead and select the ASE 7. We have it checking for the 05, the 10, and the 16 versions of the code. And then I'm going to ask the program what I want to check. I want to check for soft stories, and I want to check for irregularities. Okay, so what it's going to do is it's going to look in the tables within the code. I believe this is in chapter 12 of the ASCE 7. I have the 16 version of the code open for myself. And what this will do is it'll check the vertical and horizontal irregularities options, a few of the options from those tables, and it'll be able to print in your output file whether or not those are present for you. Now, you could enter base level of your structure. If you leave this unselected, then it's going to automatically take the base level of your system. So I'm going to leave mine unselected. Just so happens my base nodes are already at y equals 0, so it shouldn't matter for me. And then it's reminding me how many diaphragms I have in my system. This is not an editable field. It's recognizing the number of diaphragms I have. So for the irregularity checks, so we're checking for a soft story. For the irregularity checks, it's going to check for torsional irregularities, re-entrant corners, and mass and irregular modes of vibration. So let's go ahead and click OK here. And let's go ahead and see the extra information that's been added to the output file by adding those commands. Now here what you're going to notice is that now what's new is I do have a warning that's been generated. I'm assuming that I have some type of irregularity within my system. Irregularities will be listed as a warning just to kind of cue your eye into it. So let's go ahead and view our output file. And here we can see that we have a soft story detected. So warning is issued when you do have an irregularity within your system, either a soft story or a torsional check. So here again, we still have our floor diaphragm table. We still have our diaphragm center of rigidity, but now we have our irregularity checks. So let's go ahead and proceed on to the soft story. So this command will instruct the program to check for soft stories according to either the IS 1893 or the ASCE 7 codes. A soft story building is a multi-story building where one or more floors are soft due to structural design. These floors can be dangerous in earthquakes because they cannot cope with the lateral forces caused by the swaying of the building during a quake. As a result, the soft story may fail, causing what's known as a soft story collapse. So what we're going to be able to tell you within this table is whether or not you have a soft story or also an extreme soft story. You can see in my particular system that level number 1, this is referring to the rigid diaphragm number that I have, is actually technically a soft story. Now, what do I do with this information? Well, I'm definitely going to go to my building code. Again, I'm using the ASCE 7. Now, taking a look in section 12 of ASCE 7, I have vertical and horizontal irregularity checks that are listed in those tables. If I come up that I have a soft story, I should definitely check that table. That would be a vertical irregularity. And then I'm going to check to see if there are any clauses within the code that I need to also be aware of to incorporate. Let's go ahead and also take a look at our irregularity check. So here, the first one is a torsion. So this is like just the section heading. And then I have 3 different tables that represent that information. So the first one is my torsional irregularity checks. This would be for a horizontal irregularity. I think it's type 1A or 1B. That would be a regular torsional irregularity or an extreme torsional irregularity. I'm going to take a look in this table, and here I'm going to see the results, and I have the status. And so here I can see that I don't have a torsional irregularity within my system. Okay, and here we can see the torsional irregularity checks. There are the ratio limits. You'll find that directly in the code. So mine is saying, okay, okay, okay. I don't have a torsional irregularity. Next, I'm going to take a look at a geometric irregularity. This is checking for re-entrant corners. Here I can see I do have a re-entrant corner on my particular system. So I have a soft story and I have a re-entrant corner. And then lastly, I'm going to go to a mass irregularity. This is letting you know what the ratio limit is. And here my status is okay for each one of these. So what am I going to do for this with this information? Well, I'm going to look in my building code. I'm going to look in, for me, the ASCE 7. I'm going to check which types of irregularities I have. Depending upon the information that I see, I may have to consider which type of analytical procedure can I follow. I may not be able to do just a static seismic load according to the equivalent lateral force procedure. I may be required, depending upon this information, to do more of a dynamic seismic analysis. Okay. In addition to that, if I have, say, a reentrant corner, I may need to want to consider adding some notes to my drawings or some extra detailing information about detailing collector elements or fastening of my deck to my structural system. The final thing I may also want to consider is if I did have a torsional irregularity, I may need to adjust the accidental eccentricity that I'm applying to my seismic forces. I may not want to just consider 5% eccentricity. I may be required to scale that up depending upon what seismic design category I may be in. So this information will kind of help you when you get to the next phase of your design, which is planning how to generate your seismic loads on your system. What types of seismic loads, what types of eccentricities are going to be required. And so all of that is now available for a rigid diaphragm approach within STAAD.Pro. Now, within this particular model, the last command I want to show you is how to print your story stiffness. So that is available as a post-analysis command. So I'm going to select the post-analysis commands option. I'm going to go to define commands, and then I can go with story stiffness. Let me go ahead and add this and then click close. Now this command will instruct the program to include the calculated lateral stiffness of each story used to determine the drift of the structure. In STAAD.Pro, lateral stiffness is calculated only when the floor is modeled as a rigid floor diaphragm, since it functions as transferring story shears and torsional moments to lateral force resisting members during an earthquake. So one last time on this model, let's go ahead and run our analysis and take a look at the new table that we now have in our output file. And lastly, we have a new table that has appeared here. This is our story stiffness, which will give you that information that we requested. Now that we've gone through the process of modeling our floor diaphragms in STAAD.Pro using the floor diaphragm specification, and we've accessed all the different areas of the program that are now going to be open to us to ensure that we consider all of our code requirements for floor diaphragms, including things like torsional irregularities, into our system. Let's go ahead and move forward to a model that I've already completed that also has some seismic loads in it, because now what I want to do is I want to direct our attention to eccentricities. So now that we've learned how to model these rigid diaphragms, let's talk about the different types of eccentricities that you have. So this model is identical to the last one that I was just looking at, with the exception of I've already taken the liberty of creating some static and dynamic load cases and load items within this system. Let's go ahead and start by taking a look at this reference load definition. This is still my mass that I just created. It's identical to what I did before. Now, this particular model has more information than my last one did. So let's talk about what else this reference load case is going to be used for. I still have floor diaphragms at each levels, level 1, 2, and 3 for my system. And this mass is going to be used to calculate the center of mass for each level of the system. In addition to that, what you're going to notice is that my seismic definition, according to my equivalent lateral force procedure, has also been established in the load definition area. This is also going to be using that reference mass load case to determine the mass of the structure for determining the base shear of the system using the seismic definition that I created. And then lastly, I can see that I've already created some dynamic seismic load cases using the modal response spectrum procedure. These dynamic seismic load cases will also be using that mass reference load case. So it's kind of nice. I just established it one time. Everything else is using the same thing. Let's go ahead and take a look at incorporating eccentricity within our particular model. Now, we have two types of eccentricity that we may need to consider when applying or generating seismic loads for any system. The first is your accidental torsional moment, and then you also have natural torsional moment. So within the code, it may be requiring me to include accidental torsional moment. That typically might equal about 5% of your overall building dimension in each direction. Again, you may need to scale that up if you have any irregularities up from 5%, depending upon your seismic design category. In addition to that, you also have your natural torsional moment, which accounts for the static eccentricity, which is basically the difference between the center of mass and center of rigidity in a rigid floor diaphragm system. Now, our system has a rigid diaphragm, so let's talk about the things that you're going to do a little bit differently when generating your seismic loads when you have a floor diaphragm versus when you don't. The first thing you're going to notice is, let's take a look at my seismic definition. This is the seismic definition. So let's take a look at our seismic definition. Now, when considering accidental eccentricity, you do need to understand if you have a rigid diaphragm or if not. I have a rigid diaphragm in my system, so what's very important is within my seismic parameters, I'm going to include this accidental eccentricity checkbox unselected when taking a look at my seismic definition. So when creating my seismic definition with a rigid floor diaphragm, I leave this off. The reason for that is because eccentricity for rigid diaphragm systems happens in the load items, in your seismic load item. It doesn't happen in the seismic definition. This checkbox is to prepare the model in case you're going to have accidental eccentricity for a non-rigid diaphragm system. I have a rigid diaphragm system. I don't specify accidental eccentricity here. Okay, so let's go ahead and close that. So that's the first step that you're going to have to consider. Let's go ahead and take a look at our load cases here. So I'm going to start with my static seismic load cases. Now, in my particular model, I just created 2 static seismic load cases, 2 dynamic seismic load cases. Now, in the real world, you may have some additional load cases. I'm just taking a look for me at seismic load in the positive X direction with positive eccentricity, and then the same thing in the Z direction. Again, a realistic structure, you may consider more scenarios such as the negative direction or the effects of negative eccentricity in addition to that. So let's go ahead and take a look at the static seismic load. And the 2 checkboxes I'm going to turn your attention to here is your multiplying factor for accidental torsional moment and your multiplying factor for natural torsional moment. So let's start with this factor. So this is your ACC command. And what we're going to do is we're going to enter the percentage of eccentricity that you're interested for accidental torsional moment for this seismic load case. Now, for my particular model, I didn't have any torsional irregularities per se that would require me to increase the percentage for accidental torsional moment. So I'm setting my factor equal to 0.05. This would be 5%. So what the program's going to do is it's going to take the 5% of the overall building dimension in, depending upon which direction your seismic load is being applied in, and it's going to basically include that as a bit of a moment arm for that application of seismic load. The next is the option for your natural torsional moment. Now, for this checkbox to be available to you, you're going to need rigid diaphragms in your system. So you're going to see that only valid on models with rigid diaphragms that are defined. And if you do want to include natural torsional moment, what you're going to do is you're going to set this factor equal to a +1. It is always set as a factor of +1, which basically just tells the program, yes, I want to consider it. Again, the program already calculated where my center of mass is. It already calculated where my center of rigidity is. So it understands what to use for the torsional moment. This is just telling it, yes, please include that static eccentricity. Again, that'll be the difference, or the moment arm that's created from the difference between the location of the center of mass and your center of rigidity. So this is how I'm going to specify this. Now, if you do want to specify negative torsion, what you're going to do is you can enter this accidental torsional moment as a negative value. So say negative 0.05, and then that would have basically the opposite rotation effect for that torsional moment. So let me go ahead and close out of here. You're going to see that I did the same thing down here as well. Let's also go ahead and take a look at our dynamic seismic loads. So let me go ahead and highlight one. I'm going to click the edit button. And here what we're going to say is we're going to see these checkboxes to use torsion. Now, this dynamic eccentricity, this is basically refers to your natural torsional moment. And then again, you have your accidental eccentricity. You basically specify these the same way you would as your static seismic loads. You're going to give your dynamic eccentricity a value of +1 always, if you want to consider it. And accidental eccentricity, you're going to consider what percentage of building dimension is required for that moment arm. You can give this a positive or negative value. It's typically going to be 5% unless you're required to increase it from there. Again, dynamic eccentricity would not be permitted unless you have rigid diaphragms. So you can see I did that there, and actually for this one as well, you can see those factors are present there. So let me go ahead and save my model. And let's go ahead and analyze this. And I'm going to show you some of the information that you have available to you now that I've taken it the extra step to add seismic loads. So let's go ahead and view my output file. And I do have some warnings, which of course I always say you should definitely check first. Now, the first one is that I did get a warning that if this is in IBC analysis and I have tensional or compression only members, I may need to analyze each seismic load case individually. I actually don't have any tension only or compression only members in my model. I'm not using my seismic loads in any repeat style load combinations, so I can disregard this warning. I don't fall in the category that would require this. Let's go ahead and move down. And again, I still have my warning that a soft story was detected. Now, when you do a dynamic seismic, or when you have dynamic seismic load cases, you're going to also get some quick links to that information. But before we go ahead and take a look at that, let's start with our static seismic load cases. So what I'm going to do is I'm going to scroll down in my output file. And here is my floor diaphragm information. Again, I have my center of mass. Then what we're going to do is we're going to get into our static seismic load cases. So for each load case that you have that represents your static seismic load, you're going to be given a block of data that'll give you important pieces of information, such as some input values, some time period information, also your design base shear. So I have that for my two static seismic load cases. And then if I scroll on down, since I do have a rigid diaphragm, I'm also being provided this table. This will give you some more information about the eccentricities that were being used. Now, the dynamic eccentricity, basically within this table, it just reports it as 0. It's not that it's not considering it, it's that I didn't bump it up from 1.0. Now, there are some design codes. I think the Indian Design Standard, and anybody can correct me if I'm wrong, may require you to kind of amplify this dynamic eccentricity. If I had amplified it, it will go ahead and be reported there, but it is being considered, even though it's not in this table. But what I can see is I can see my accidental eccentricity. So for me, what I did was I took 5% of my overall building dimension in each direction for a seismic load. You could easily verify this information with this table to make sure that your moment arm is exactly what you were anticipating. And you can use this to kind of understand what STAAD.Pro takes as the overall building dimension in that direction. I believe it uses the coordinate values for all of the nodes within that particular level. So basically, if you take your minimum and maximum node, take 5% of that, that should equal in this direction 3.5 for the X direction, and then the Z direction, it should equal 2 feet, for example. So I do have this information available for each of my static seismic load cases. I specified my eccentricity exactly the same way for both of them, considering both dynamic and accidental eccentricity in my system. Let's go ahead and scroll on down, and I'll be able to see, of course, all of the information for my dynamic information, such as things like participation factors. And let's see if there's anything else that might interest you. And I have some, again, some eccentricity information for my dynamic loads as well. Here I'm given each level of my structure, the diaphragm it represents. And actually, this is giving me my overall plan dimension. So if you wanted some more information, and then again, my accidental eccentricity numbers. So all of this is supplied. I didn't add any extra post-processing commands in the file. It went ahead and provided this for me. And again, I have my peak, additional torsional moments available.